What up, athletes? Whoop, whoop. Welcome to 4.4 Transformations of Linear Functions. All right, the learning target today is I will identify the effects of transformations of the graphs of linear functions. Take a minute, look at the warm-up. Does each situation describe a translation? Translation is just a move. Don't get too freaked out by it. It's just a move. Does it describe a reflection, like looking in the mirror? You know what I mean? That reflection. Or does it describe a rotation, rotating? And the last one it can describe is a dilation. Dilation is like where we make something bigger or smaller but keep the same proportions. Okay? We'll talk more about that in time to come. Go ahead and write these down. Ready, set, go. The famous coffee sound. All right. I'm going to assume you paused this, did it, whatever you need to do. Using a screwdriver, that's a rotating movement. So that's a rotation. Using a sewing machine to sew a seam, it's just a straight movement. So that is a translation. It's just that movement, translation. The image of a mountain on the surface of a lake. It's like a glassy mirror, so that's a reflection. Architectural models, like when they build a model of, let's say, a mall they want to build. They build a smaller model, but it's actual dimensions. That's proportional. It's called a dilation. They've dilated it down, or can sometimes dilate things bigger, right? That is a dilation. Dilation. Oh, just a DI. Who knew? Movement of cars down a highway, again, that's just that straight movement. That's all they're doing, so that is a translation. Okay, let's go take a minute, look at our vocab. We have a family of graphs. Graphs and equations of a graph that have at least one characteristic in common. So like the graph, which we'll talk about a lot today, is f of x equals x, or y equals x, right? Is a family. It's a parent function of y equals x plus 3, or y equals 3x. They all have that x in common. Parent function is the simplest of functions in a family, so it's just that base, like that f of x equals x. Just the x there. There's nothing added to it, multiplied by it, right? Translation is a transformation in which a figure is slid from one position to another without being turned. Okay, it's just that slide. Reflection is a transformation in which a figure, line, or curve is flipped across the line. In math, we do that with the negative. Talk about that. If we negate the x, then we do a flip across the y-axis. If we negate the y, we do a flip across the x-axis. If we negate both, we flip across both axes. So we're going to talk about that. Pause this, write these down. I am moving back to the worksheet where you can see clearly I've filled it all out ahead of time. You could have seen that before. Since describe the translation in g of x equals x minus 2 as it relates to the graph of the parent function, f of x equals x. Guys, don't get so worried about these f of x equals x and g of x equals x minus 2. Remember, these are just substitutions for y. That's why down here you see the coordinate. Instead of xy, it's x g of x, right? The difference is this allows us to tell which function we're talking about. This is the parent function. It's the base level function with x, right? Just that straight through 0, up 1 over 1, boom, nothing special. Now we've done minus 2. What did minus 2 do to this graph? Well, look, you can kind of follow these arrows. It moved everything's the same, got the same slope. It's still up 1 over 1, right? It's got the same everything. The only difference is it moved down 2. The start value is negative 2, so that just kind of takes the graph and moves it down. So when we add or subtract numbers here, it's going to either move the graph up or move it down. Okay? So what did it do? It moved the graph. Or I would say instead of move up here, let's put, about right above it in parentheses, put translated. Because it is a translation. The graph down. Down is another important word. 2 units. Okay? So that's a translation. When we add or subtract over here, it's going to translate it. Now I want to talk about a dilation here. So this is a translation. We're just adding or subtracting to the parent function. You see it moves everything down a little bit, okay? Where we had originally, it would have been 0, 0. Now it's 0, negative 2. It's down to where it would have been 1, 1. Now it's 1, negative 1. Where it would have been negative 2, negative 2. Now it's down 2 to negative 4, okay? Now let's talk about a dilation. So this is a translation. I know we wrote over there, but a translation. And now we're going to talk about a dilation. Man, I keep wanting to put dilation. Okay? And we're looking at the dilation g of x equals 2x. See, we've multiplied that x by 2 as it relates to the graph of the parent function f of x equals x. We're just saying, this is a parent function again. Just means we haven't done anything fancy. It's just x. It's that base level. Okay? Boom. We have it again right here. Now, let's take a look at, notice the line has become less steep or more steep? Boom. More steep. And that more steep is called a vertical stretch. So I want you to look at kind of my little square there. So when we dilate something, there's one of two things we can do. We can either vertically stretch it, where all I'm going to do, notice, this is the distance my hands are apart. I'm going to move up, and I'm going to keep my fingers same thing apart, except I'm stretching. I'm just moving it straight up, and the more I move it up, the more it stretches and becomes steeper. Or we have a thing called a vertical compression. Vertical compression becomes less steep. So let's write that down. We have a vertical stretch. Graph becomes steeper. And actually, this occurs when the number multiplied is greater than 1 or less than negative 1. So there's two kinds of steepness, guys. I want you to think about this. There's a steepness that makes it a, let's see, well, I guess that's a negative, so if I go opposite, because I'm in the mirror. There's a steepness that makes it positive, right? See how that's becoming steeper in the positive direction? But also, if I multiply by something less than negative 1, it's going to become steeper in the other direction and become negative. So just keep that in mind. That's why it can be greater than negative 1 or less than negative 1. Then we're going to have a vertical compression. Vertical compression is when the graph becomes less steep. And this occurs when the number multiplied is, I'm just going to say when the number is less than 1 but greater than negative 1. In other words, it's a fraction or a decimal. Fraction or decimal. Okay? And it has to be a fraction or decimal that's, again, less than 1 or greater than negative 1. It's just kind of in between that area there. Now we can see right here, this has become more steep. So that has become vertically stretched. We've stretched it, right? We've taken this rubber band, our graph that was right here. Where are we at? Right here. And we just stretched it to make it more steep. That means what we multiplied by was greater than 1 or greater than negative 1. And look at that. 2, because it's greater in the positive direction, that's greater than 1, because if it's greater in the negative direction, it becomes negative. That's another vertical stretch. Actually, it's all vertical stretch. It's just going to end up flipping it too, which is called reflection. We'll talk about about that in a minute. So notice right here, where originally it would be -2, -2, we multiplied it by 2, and that became -2, -4. Where it was originally 0, 0, that doesn't change. Anything times 0 is still 0. But where it was 1, 1, that 1 times 2 becomes 2 right here. Okay? So this is a dilation. And we're almost done for today. I'm going to get back to some more review. It says, let's just move it on up here. Describe the graph of g of x equals -0.5x here as it relates to the graph of the parent function f of x. I did forget to say over here, by the way. What is this? This is a vertical stretch. I said it, but we should probably write it down. Okay. Oh, can't even see that. This is a vertical stretch, okay, because it stretched it up. I want to say that because over here we're going to have the opposite. We're going to have two things going right here. One, notice this is -0.5. So the multiplier is -0.5, right? Therefore, this is a vertical compression. But really, two things are going on right here. We're having two effects on this. So I want to talk to you about what that is. So if it was just 0.5, then that original, so if we have, I'm going to do an h of x. H of x equals 0.5x. So if we would have had that point, x is -2, then what's half of -2 for h of x? Well, half of -2 would be -1. If I have 0, it's still going to be 0, but if I have 4, what's half of 4? It's going to be 2. So let's graph these points. So I would have -2, -1, 0, 0 still, and then 1, 2, 3, 4, up 1, 2. I'm drawing this on purpose because I want you to see the two different transformations happening on the graph right here. So this is my h of x, right? This is the one I just made right here. Notice that h of x right here is less steep. So if I take my rubber band example again, I have compressed it, right? And I've made it less steep. But g of x had something else added onto it. G of x is -0.5x. So again, notice that because we're multiplying by that -0.5 times the x, it's making all the y values switch, which is actually reflecting this across the x-axis. So where normally I would have multiplied by 1/2 and got 2, what am I going to get? I'm going to get -2. Where I would have multiplied -2 by 1/2 and got -1, now because I multiplied by -1/2, I'm going to get +1, which we're seeing over here. So that's actually a reflection across the x-axis. It's making those y values switch. So where y would have been up here, now y is going to be down here. And you'll notice that this is 2 away, and now it's 2 away because it negated that. This is 1 from the x-axis, this is 1 from the x-axis. So that's a reflection across the x. Okay?